Today at first, what we're going to do, before we get into what we're actually, the new stuff that we're going to do, we're going to look at and review limits. Remember, as the limit went off to infinity, if it had a horizontal asymptote, it would go off to that horizontal asymptote. All right, so here what we looked at was, all right, we have 4x over 5x. We looked at what was carrying, like what carries the top here, 4x, and then what carries the carries it down here, 5x. And if I did 4x over 5x, that gives me 4/5. Or if you just think about the horizontal asymptote. Okay, for this one, if we look at what's carrying, we got the 4x over the 5x squared. Okay, which would be 4 over 5x. And as x goes to infinity, the denominator gets really, really large. So eventually this goes to 0. Or think about it. The horizontal asymptote is 0 here. Okay, what about this one right here? Okay, what carries the top and what carries the bottom? And we end up with 4x squared over 5. However, as the numerator goes off to infinity, therefore the whole limit goes to infinity. And then also we looked at limits like this to where you could factor. All right, this factors as x plus 3, x minus 2. And here, the x plus 3's cancel, and then we can say, okay, when I plug in -3, I end up with -5. So the limit as x goes to -3 of that ends up being -5. Well, not all the time are finding limits going to be this easy, and we can't always look at the horizontal asymptote, or we can't always look at, everything's not going to be factorable. So what we're going to use is something called L'Hopital's rule. All right, limits can have something called indeterminate forms. This means you can't determine the limit. And these are the different forms, like 0 over 0, infinity over infinities. And what that means is the numerator goes to 0, the denominator goes to 0. Here the numerator goes to infinity, denominator goes to infinity. And then these are some other forms. For AB, we only focus on these two forms. For BC, we do focus a little bit on these, but it's not going to be as prevalent. All right, and what L'Hopital's rule, it allows us to find the limit of expressions that gives us indeterminate forms before we tried to rewrite it. Okay, so we tried to factor it. All right, to solve. But not all indeterminate forms can be algebraically manipulated. So this is where we use L'Hopital's rule. L'Hopital's rule can be used to find the value of a limit that after substitution are in the indeterminate form. Okay, and it says this: as we have a limit that either goes to c or infinity of f of x over g of x, it's going to equal the limit as x goes to c or infinity, whatever it's going to. We can actually take the derivative of the top and the derivative of the bottom. Okay, and I want you to make a note. This is not quotient rule. All right, so I first want to take a look at limits that we just did. Now, please, please, please pay very special close attention to how I write this. One of the things on the AP test, and this has changed in the last couple of years, they don't want to see you say equals 0 over 0 or infinity over infinity. We can't write that. Now, we know this answer is 4/5, but I want to show you this, and I want you to show you L'Hopital's rule. Here, we could say this numerator, the limit as x goes to infinity of the numerator of 4x plus 1, well, look, it goes off to infinity. And the limit as x approaches infinity of 5x minus 6 also goes to infinity. So, because this would be infinity over infinity, this is an indeterminate form, I need to use L'Hopital's. So, guys, they expect you to have this type of work here. The more you do it, the more comfortable you'll come at it. Okay, so what we're going to do, I'm going to rewrite my limit over here. We'd say, and keep your limit notation, the derivative of the top, again, it's not the quotient rule, over the derivative of the denominator. And look, this is just a constant here. And the limit as x goes to infinity of a constant is just that constant. And isn't that what we got for number 1 to begin with? Yeah, we got 4/5. Okay, so let's look at this one as well. The limit as x goes to infinity of the numerator goes to infinity. Well, the same thing. The denominator also goes to infinity. So therefore, we can use L'Hopital's. So here we go. Now, they always want you to equate, and that's why I'm rewriting this to L'Hopital's once I've taken the derivative. All right, because they want you to show that these are equal. So the derivative of the top is 4, derivative of the bottom is 10x. All right, and as I put infinity, as this gets larger down low, this will go off to 0. And that's what we got before. So let's look at some forms that aren't as easy to do, and I have to use L'Hopital's on. Okay, so let's look at this right here. The limit as x goes to infinity, to 0, sorry, of 1 over 2 plus x minus 1 over 2, all right, and then x. When I start looking at this and I see 0, I see, wait a minute, 0. That's going to be 1/2 minus 1/2, so that goes to 0. And then when I plug 0 in here, that goes to 0. So I know I'm going to have to use L'Hopital's. There's no, maybe I can multiply by the common denominator. I'm just not even going to mess with it. I'm just going to do this right here. I know this numerator goes to 0, so you have to show it. And I know the denominator goes to 0, which is x. It also goes to 0. All right, so therefore I have to use L'Hopital's. All right, so what I want to do is keep your limit notation, or they'll take off. I have to do the derivative of the numerator. Now, this is like 2 plus x to the negative 1. Okay, that would probably be the easiest to do. So I get negative 1, x, 2 plus x, or x plus 2, to the negative 2. And then when I take the derivative of 1/2, that's just 0. Over, what's the derivative of x? 1. So look, this is the limit as x approaches 0 of negative 1 over x plus 2 squared. Now, let's think about it. Can I plug in 0 now? Yeah, I can plug in 0 now, and when I plug in 0, negative 1 over, it ends up 2 squared, that equals negative 1/4. All right, let's go look at another one. Now, remember I told you the other day, or the other unit, that sine x over x, as the limit as x goes to 0 of sine x over x, what do you remember that is? It's 1. Well, let's verify that, that it is 1. Well, here, again, L'Hopital's, I know it's kind of redundant, and you're like, I don't want to do this, but please do. As I plug in 0, this goes to 0, and the limit as x approaches 0 of x also goes to 0. So I've got to use L'Hopital's. Okay, so I say the limit as x goes to 0, take the derivative of the top, that's cosine x, take the derivative of the bottom, okay? And now when I plug in 0, I'm just plugging in cosine of 0, I get 1, all right? And it was 1. Okay, moving right along. Here we go. And again, as I write these, if you want to try some on your own, feel free to. So let's look at this. Okay, the limit as x approaches infinity of ln of x. All right, well, if we go to a graph on that, you'll realize that goes off to infinity. And the same thing of x cubed, it also goes off to infinity. So that's that indeterminate form, infinity over infinity. So I can use L'Hopital's. All right, so I'm going to take the derivative of the numerator. Again, it's not the quotient rule. 1 over x over. Okay, and then this is going to be 3x squared. All right, so when I reduce this, this is 1 over 3x cubed. Okay, now as x goes to infinity, think about it, the denominator gets really, really big. So therefore this goes to 0. The problem was this ln of x right here. All right, let's go do a different one. Okay, the limit as x goes to infinity of x over e to the x. Well, here the numerator goes off to infinity and the denominator goes off to infinity. So, and this is exponential, remember that. We're going to, you got to write it down. So therefore I'm going to use L'Hopital's. Okay, so now limit as x goes to infinity. The numerator, the derivative is 1. Denominator, the derivative is e to the x. Okay, so now the numerator is now going to 1, and when I plug in infinity here, okay, or larger numbers, as they get larger, what happens to our denominator? It gets larger. So therefore, the limit goes to 0. All right, moving right along. Let's look at the limit as x approaches 0 of e to the 2x minus 1 over x. Now this one, when you start plugging in, you realize, okay, that ends up e to the 0, but e to the 0 is 1, 1 minus 1 is 0, and then if I plug in 0, that's 0. So therefore, I'm going to go ahead and write it out. That goes to 0. All right, and that goes to 0. So we're going to use L'Hopital's. All right, so let's think about it for a second. You got to take the derivative of the numerator. That's e to the 2x, and then don't forget the chain rule, times 2. Over derivative of the denominator is 1. So really, I'm just looking at the limit as x approaches 0 of 2e to the 2x. So think about it. 2e to the 2 times 0. Well, e to the 0 is 1, so this just goes to 2. All right, here we go. The limit as x approaches infinity of e to the negative x square root of x. Now, I would rewrite this because the problem is I don't see anything in the denominator. So it looks like that. So you have a function on top and a function on bottom. All right, so here the numerator, the limit as x approaches infinity of the square root of x goes to infinity. And the limit as x approaches infinity of e to the x also goes to infinity. So we're going to use L'Hopital's. I know, still redundant, but get in the habit of writing it this way. You've got to. Okay, or they count off. All right, so here we go. Think of this as x to the 1/2. And guys, don't put equals. Use arrows when you're not sure if you should do equals or not, because you want to be mathematically correct. All right, so this is 1/2 x to the negative 1/2 over, all right, just e to the x. Okay, so this gets rewritten, and I'm going to rewrite it down here. Limit as x goes to infinity of 1 over 2 square root of x e to the x. Okay, so now I have a 1 on top. All right, but in the denominator, if I plug infinity, this part goes to infinity, that part goes to infinity, but because it's in the denominator, it eventually goes to 0. All right. Let's look at another one. Okay, the limit as x approaches infinity of ln x to the fourth over x to the third. Well, here, if I plug in an infinity, that goes to infinity and this one goes to infinity. So the limit as x goes to infinity of natural log of x to the fourth equals infinity, and the limit as x approaches infinity of x to the third also goes to infinity. So we're going to use L'Hopital's. Okay, so here we go. Derivative of the numerator is going to be 1 over x to the fourth times 4x cubed. Okay, denominator 3x squared. So this makes, let's see, that goes away. And what this x ultimately goes down low. So that's limit as x approaches infinity of 4 over 3x to the third. All right, so therefore, here as x goes to infinity, this goes to 0. All right. The limit as x approaches infinity of x tan over 1x. Now, this one is a little confusing and you're like, I have no idea. Well, here, this one goes off to infinity, but that one, or no, this one goes to 0 and x goes to infinity. So that's an indeterminate form. But you're like, well, I don't have something in the numerator and something in the denominator. So you can actually rewrite this. So it's tan of 1 over x. Okay, and then you can change that x to be 1 over x. Here, tan goes to, it's 1 over x. So as this gets larger, really that just goes to 0. So the limit as x goes to infinity of tan of 1 over x equals 0, because tan of 0 is 0. And the limit as x approaches infinity of 1 over x also goes to 0. So it's the indeterminate form. Okay, so now if I take the derivative of the numerator, all right, derivative of the numerator is going to make secant squared 1 over x times, now just be careful here, you got to take the derivative of 1 over x and think of that as x to the negative 1. So it's going to be negative x to the negative 2 over. Now again, this is x to the negative 1, so that's negative x to the negative 2. And what do you recognize happens? That goes away. All right, so the limit as x approaches infinity of secant squared 1 over x. Okay, now you got to think about this for a second. This goes off to infinity, that's going to be 0. But remember, secant is 1 over cosine. So think of this as 1 over cosine squared of 0, but what's cosine of 0? 1. So this whole thing goes to 1 right there. So these are the ones that you're really going to focus on in AB because it's going to be 0 over 0 or infinity over infinity. I do want to look at some for like 2 of them for BC. So if you're AB, you may cut off the video. If you're BC, let's keep going. Okay, and I'm going to do 2 more. All right, for BC, the limit as, and let me find the one I want to do. Okay, as x approaches 0 from the right. All right, if you actually think about this and you're plugging in 0, all right, you end up with 0 to infinity. All right, because if you think about this for a second, and the reason why this is infinity, think about the graph of 2 over x. from the right, it's going off to infinity. Now this is that indeterminate form. Now anytime you have any of the indeterminate forms where you have like something raised to the something, we want to use logs. So what I'm going to do is I'm going to set this equal to y. And I'm going to take the natural log of each side. So the natural log of y equals. Now I have to keep limit notation. And then I'm going to say the natural log of e to the x plus x to the 2x. So the natural log of y equals, all right, and what I can do is I can actually bring that 2 over x and use the power property. Well here, if you look at it, well if I plug in 0, this is going to be ln of 1. Well, ln of 1 is 0. So the limit as x approaches 0 from the right of 2 ln of ex plus x is going to equal 0. And then right there, the limit as x approaches 0 from the right of x equals 0. So here, I'm going to use L'Hopital's. All right. Now again, you have to keep that limit notation. Now, what we're going to do is we're going to take the derivative. I'm going to keep a limit. Now, I want you to pay attention to this because this is going to come back later on. All right. When I take the derivative of the top, it's going to be 2 times 1 over e to the x plus x. And then you're timesing it by e to the x plus 1. All over 1. So now remember, this is ln of y. I'm going to rewrite that. So this equals the limit as x approaches 0 from the right, okay, of basically 2 e to the x plus 1 over e to the x plus x. Okay, well now let's think about it. Can I plug in 0? I can. And so this is going to be 2 e to the 0 plus 1. And then e to the 0 plus 0. Okay, well down here is just 1, and then up here that's going to be 1 plus 1, which is 2. So 2 times 2 is 4. Now, here's my issue. That's not what y is. Y is what the limit equals. Okay, so, and I shouldn't have put equals up here. I should have put an arrow. Okay, because that's wrong if it's written like that. Okay, so what I'm going to do is take the natural log of y and set it equal to 4. And I have to solve for y. All right, well, how do I get rid of ln? E. So y equals e to the 4th. All right, so what that means is this limit that it was set equal to y from the beginning, that limit goes to e to the 4th. So we added that extra logarithmic differentiation in there to help us out to find that limit. All right, and let's do one more. The limit as x approaches infinity of 1 plus 1 over x to the x. All right, if you look at this, okay, if it goes to infinity, this is going to be 1 to infinity. Again, I use the arrow, don't put equals. So this is an indeterminate form. Now I got this raised to the x. So what I'm going to do is I'm going to set this equal to y. And if I use logs, okay, I'm going to go ahead and save myself some time. And I'm going to go ahead and bring that x down. Now I'm going to want to change this so it's the natural log of 1 plus 1 over x and then 1 over x. So I have a numerator and denominator. And when I look at it, when I go to infinity, this goes to 0. I'm left with the ln of 1. So therefore the limit as x approaches infinity of the ln of 1 plus 1 over x goes to 0. And the limit as x approaches infinity of 1 over x also goes to 0. So therefore, I'm going to use L'Hopital's. All right, so here we go. I still have ln of y. I got to take the derivative of the numerator. Okay, so keep your limit notation. Okay, so it's going to be 1 over 1 plus 1 over x times the derivative. Now recall that that's x to the negative 1. So that's going to be negative x to the negative 2. It may work its way out like it did in one of those other problems. And here the derivative of this, remember, that's like x to the negative 1 again. So the derivative of that is negative x to the negative 2. And it does. These are going to cancel. So I'm going to be left with the limit to x approaches infinity of basically just 1 over 1 plus x. Or, sorry, it should be 1 over x. One of the things you could do to clean this up a little bit, you can multiply by x, but upon looking at it, think about as if we're putting this into infinity and here, this part goes to 0. Okay, so really this limit goes to 1, but recall this is the ln of y equals 1. All right, that's not what the limit is, and remember that's set equal to y. So we got to solve for y. We need e, so y equals e to the first. Or we could just say e. So therefore, the limit as x approaches infinity of 1 plus 1 over x to the x equals e. All right, so BC, you're going to have to go a little bit further, and you may, for some of these other indeterminate forms, you may have to use logarithmic differentiation. Just stick with it. Make sure you keep your ln, and in this case, the last two cases, I had to solve for y and then set it equal. Make sure you set it equal so they know. And also for L'Hopital's, don't forget all the different, you've got to show that the numerator goes to 0, the denominator is 0 or infinity, and that you're going to use L'Hopital's, because that gives you probably about 2 points right there on an exam. All right, and then you need the work till you get to your answer.